Yeah, I think we are live. Hi everyone, welcome to the last session of our conference. We are together with Alper Yegin. My name is Tuncer Baykaş and I am the Vice Chair of IEEE Turkey section. So Alper Yegin is a technology architect involved in research, design, standardization of IoT and mobile technologies. He's currently serving as the Senior Director of Standards and Advanced Technology Development at Actility, the leading system vendor in the IoT LPWAN field, and Vice Chairman of the Board of Directors and Chairman of the Technical Committee at the LoRa Alliance. Prior to his current post, he has worked for Samsung Technologies Research Center, where he led 5G IP mobility, 4G WiMAX security, and ETSI M2M security design projects. He has made essential contributions to the design and standardization of networking technologies. He is past member of the IETF Wireless and IPv6 Forum Technical Directorates, and author of numerous telecom-related standards and papers with 16 granted and several pending patents. He is also working for the IoT R&D ecosystem in Turkey as the founder of the IoTxTR, and he has been organizing and teaching an IoT course at Bogazici University. So welcome to IEEE conference. Today's topic is unlocking the massive IoT requires wireless communication technologies that are low power and long range, secure, scalable, and low cost. So LoRaWan proves to be the technology that fits the bill passed on these technical features and market traction. In this talk, Alper will be covering the driving use cases, technical features, and current implementation and deployments across the globe, and evolution and near future developments of the LoRa Alliance and the competitive landscape. So the floor is yours, Alper. Thank you.
Thank you very much, Professor Tuncer, for this introduction. Hello, everyone. Good evening, good afternoon. So it's a pleasure to be here to present this very exciting technology that I have been working on for the past 5 years very intensively. Well, in the land of IoT, obviously we're working wireless communication technologies. And in order to provide the best autonomy to IoT devices, we really care to have a low power consumption. And for a long while, we already had such wireless communication technologies, such as Bluetooth, Zigbee, and Z-Wave. Now, while such technologies provide low power consumption, their gotcha has been the short range in the order of like tens and hundreds of meters. And whenever we needed to have a longer range connectivity, we had to resort to 2.5, 3, and later 4G communication technologies. Now, while getting long range out of such cellular IoT technologies, what we've been lacking was the low power consumption. So for a long while, we had a significant gap in here, meaning a low power technology that would provide long range. And there has been several proprietary technologies filling this gap, but we did not have a standard technology. And as you all know, a standard is needed in order to lower the cost and increase the quality and have a competitive landscape to have a healthy ecosystem. And this is exactly where the LoRaWan technology comes into the picture. Given that this is a solid market need, there's a market pool, companies have moved in to fill this gap, and a bunch of them started this ecosystem called LoRaWan. And obviously, you might have heard there are also other competing technologies such as Narrowband IoT and Sigfox. So historically, where this technology came from, in fact, it came from a very small startup in France, a 4-person startup called Cyclio that has developed the RF technology, the modulation. The LoRa stands for long range, and this RF modulation has been developed by Cyclio. And seeing that this technology had real market chance, the American semiconductor company Semtech has acquired them. And a little later, Semtech came together with the company that I work for, Actility, and the IBM, and a little later, several others, to form the so-called LoRa Alliance, the ecosystem, the alliance, the industrial alliance that's behind this technology. And that is what brought us this technology to the current state. Well, if we look at the network architecture, it's a very familiar architecture. We have a radio network that's composed of so-called gateways. In the LoRaWan land, we call the access points or base stations gateways or radio gateways. They can be outdoor or indoor gateways, like picocells indoor and microcells outdoor. And this radio access network is controlled by a core network, which is most of the cases it's just a single server, a network server, that typically resides in the cloud. It can also be running on an appliance on site. And on the terminal side, we have a plethora of devices, all sorts of IoT devices that are sensors and actuators and the mixes of both. And at the end, what we really do is to connect these devices to application servers in the cloud like Amazon, Google, IBM, etc. And as such, at this level of detail, it's pretty much what you're familiar with, the Wi-Fi and cellular and all that. It's a very similar architecture. Now, if we start diving into more details, if we look at the technical features, well, what we have is a long range that also provides deep indoor coverage. And I have a few slides on that with more details. And while having long range, we also have low power, meaning that for the kind of sensors we're supporting, you can have up to 10 and even beyond years of lifetime without having to change the batteries. And it comes with a very strong security, AES 128-bit security. That's the level of security you have with Wi-Fi and cellular networks as well. Now, one of the outstanding features of LoRaWan is the use of unlicensed band. So just like Wi-Fi, where you can go and buy an equipment and plug in at home or in the office, you can buy a LoRaWan gateway and plug it in wherever you like without having to acquire a costly license. Unlike GSM, right? If you want to operate a GSM network, you need to have a license, and there's always a limited number of licenses in any country, and you would have to bid for that. And if you're not one of the owners of the license, there's no way you can build a GSM network. So with the LoRa, anyone can build a LoRa network, all the way from a small residential to a nationwide network. And as such, it lets people build public and private networks. I have a network at home that I use for my own sensors. And then in the coverage where I am, that could also be a public network that would be providing me connectivity at a fee. And the LoRaWan networks also come with a very low cost infrastructure. The reason is this technology has been built from ground up for massive IoT, meaning that serving millions and billions of devices. And also each device at the end would not generate huge amount of revenue, unlike the cellular phones we're using that generate like $50, $100 a month bill, right? There's none of that for the IoT devices. So in order to build networks that can practically infinitely scale without really bankrupting the users, we had to build this technology around a very low-cost infrastructure. And we're using open standards. The standards we're generating in the LoRa Alliance, anyone can download them, and they're open source implementation, and they can use for any research, academic, and also industrial purposes. So let's dive a little bit more into details. Let's look at the technical features. The modulation is called LoRa. It stands for long range, the short for long range. It's based on a spread spectrum modulation. Actually, it's chirp spread spectrum. It's very similar to what's been used in the radar technology. As such, it has pretty good immunity to interference. And the frequencies we're using are sub-gigahertz. In Europe, it's 868 megahertz, and in US, it's 915. And in parts of Asia, it's around 920, 923 megahertz. The channel bandwidth we're using is between 125 and 500 kilohertz. And the data rate we have is pretty low. It goes as low as 300 bits per second and can go up to 50 kilobits per second, but you don't see megabits and obviously not gigabits per second. And the reason it's really low cost is, first of all, in order to have the kind of range we have to keep the data rate low. And luckily, this kind of data rate is sufficient for the type of IoT use cases we're catering. So you cannot really run video streaming or audio streaming over that, or super large file download, but you can serve several types of IoT use cases using this. And the gateway sensitivity we have is -142 dBm, which gets us a pretty long range and the ability to penetrate through walls. Again, where we are really constrained, another constraint is the payload size. It can be as low as 11 bytes and up to maximum is 242 bytes. Again, this constraint is also stemming from the use of ISM band. So even though you don't need to have a license to use the sub-gig ISM band, there are still regulations that limit how much data you can push through that channel. There are constraints like duty cycle limitation, dual time limitation, that dictates how much data you can carry over a given period of time. So that's why we have pretty low payload size. Now, the communication type is bidirectional. We call it uplink and downlink communication, as needed for not only sensors but also actuators. And we support roaming. I have a slide on that, and also a feature called geolocation. So if you have any questions, you can already start typing them on the Ask a Question window, and then we'll get to your questions. All right. Now, in terms of the range, now, in the most challenging case of a dense urban situation, like Manhattan, as you see in this photo, the range goes down to like 1 kilometer. And if we even make it even more challenging, say we're talking about metering application, like gas meters and water meters that are like inside the buildings and at times really like behind a couple walls. In that case, the range can go down to like 600, 700 meters. But as you get out of the dense urban to the urban and country, the range starts opening up. And if you have full line of sight, the range goes all the way up to like 500 and 600 kilometers. That's what you are seeing in the second figure here. This is what we have right now. There are 2 LEO satellites spinning around the Earth, 500 kilometers above the ground, and they have LoRa gateways on them, like LoRa base stations. And using those LoRa gateways embedded inside the LEO satellites, we're able to demodulate the uplink frames sent by the sensors on the ground using the same frequency and the same transmission power as regular LoRaWan devices. So this kind of use case is where we have sensors in extreme remote areas, like in the middle of the ocean, at the top of the mountains. That's where there wouldn't be any terrestrial radio networks, and then you would have to fall back to using satellite-based coverage. And then if we apply this to indoor, where we can use very low-cost picocells, and these are basically devices just like Wi-Fi access points. With them, you can place 1 picocell every 4th floor inside the building and have full coverage inside this structure. So in other words, a picocell can provide coverage 2 floors up and 2 floors down. And by adding many of them across the building, you can have an enterprise, a private use network. So that's what we have in terms of range. Another really powerful feature of LoRaWan is microdiversity. So unlike other technologies, the gateways we have are stateless. As such, whenever a device like this meter sends an uplink frame, any LoRaWan gateway within the coverage can demodulate this uplink frame. So like in this case, only 1 gateway is out of range, but 3 gateways are in range with respect to this meter, and the uplink frame would be demodulated, in other words, received by every one of these gateways, and they will send the demodulated copy to the cloud server. That server would deduplicate that frame and send a single frame to the application server. Now, if we compare that to what's happening with, say, in urban IoT LTE-M, 5G, or Wi-Fi, the access points or base stations are stateful, and each terminal attaches to a single access point. And even though other base stations or access points could receive the signal, they would not demodulate and they would not consume that uplink frame. So in a way, that would be like a waste of radio resources in the vicinity. And this feature itself makes, well, it lowers the cost of building a radio network, because through that, we can build even less dense networks than the competing technologies and still have much better coverage, because despite the changing RF conditions, we will always have one or more gateways receiving the uplink frames, and that will be sufficient to have very high connectivity for these IoT devices. Another benefit of microdiversity is the geolocation feature. Because we can have multiple gateways demodulating the same uplink frame, now we use a TDOA-based geolocation feature. So TDOA stands for time difference on arrival. So we know where these gateways are located at the time of installation. And these gateways also have GPS receivers so that they have a very highly accurate clocks. So whenever they receive an uplink frame, they put a nanosecond granularity timestamp and push that as a metadata to a cloud server. So the cloud server gets the same uplink frame from 3 different LoRa gateways, and it knows the location of the gateways, and it knows the timestamps. And using that, it runs an algorithm to figure out where that device might be. Now, the kind of granularity we get is not super high. The geolocation accuracy is between 20 meters and 100 meters. So it's not something you would use for looking for your lost keychain or for your lost pet, unless your pet is a cow in the field. Then you would use this technology. Or if you are looking for, say, machinery at a construction site, or you're tracking trucks that are like driving across the nation, then you would certainly use this kind of geolocation feature. Now, this is a very low-cost geolocation feature because you don't need to put additional hardware on the end device. All the end device has to do is to send regular uplink frames, and you don't need to consume more battery like running GPS. And as such, it has a nice sweet spot in terms of accuracy versus cost for geolocation. And roaming. We have the roaming in the traditional sense, like say you're running a nationwide network in France, you have subscriber devices that are on a truck and they cross the border to Switzerland, so they leave your coverage area. Now, as an operator in France, if you have a roaming agreement with an operator in Switzerland, then when the truck is in Switzerland and the sensors are still sending uplink frames, say they're sending their locations, those uplink frames would be demodulated by your roaming partner, that Swiss operator. And because the Swiss operator knows that these uplink frames belong to you, and it has a roaming agreement with you as an operator, then it'll push those uplink frames to you through the backbone. This is just traditional roaming, and we have that. But on top of that, thanks to microdiversity, what we can do is we can even have the device roam into multiple networks simultaneously and also be at home and roaming at the same time. So imagine there are multiple overlap networks. Like I have my own base gateways, and I have 2 of my roaming partners with their gateways in the same area. When the device sends the uplink, my gateway will demodulate the uplink and as if the device is at home. But then my roaming partners will also demodulate, and they will send their copies to me. So it's like the device is at home and roaming into 2 other networks at the same time. So effectively what this really is it's like 3 networks, they come hand in hand. They use their radio networks collaboratively, collectively to act as one. So this is the collaborative nature of the roaming we have with LoRaWan. Again, this is only possible due to microdiversity, which is like a physical broadcast and allowing multiple networks, multiple gateways that may belong to multiple networks be able to demodulate the same uplink frame. All right. In terms of security, well, we have all the bells and whistles you would expect from a modern wireless communication technology. As you know, in wireless, we cannot rely on physical security, so we have to use cryptography. And with the cryptography, we have to have the right tools, such as having mutual endpoint authentication, data origin authentication, integrity protection, replay protection, data encryption. And one should use them with the strongest possible and practical cryptographic suite available, which is AES-128 today. And on top of that, we also support firmware update over the air. Now, this feature is basically it provides the ability to push the firmware file to the end device so that it can update its software, like the communication stack or the application running above that. Why would you need that? Well, at least because you will have new features along the way, and you don't want to recall the devices or go and visit them one by one, because they would be in the field, and visiting them in close proximity would be very costly. So you would like to update their software remotely. And not only having new features, but one way or the other, you would have some security issues, right? Something in your application that you had forgotten or you had not overseen, and some, black hat or white hat hacker will exploit that. You'll discover that, right? You'll have to patch the device in the field. And only if you have the photo feature, you can patch them in the field, which provides you an insurance or being future proof, right? So we have this ability, and we do that very efficiently thanks to, again, physical broadcast. We're able to push files to tens and thousands of devices all simultaneously by putting them on a synchronous plan so that they all listen at the same time when we transmit the frames, and they can add these fragments up to form the whole firmware. And then the last piece of security we have is hardware level security. For the sensitive application where they may be a target to hacking, like metering, right? Meters are like cashiers. Every month, they're like printing money for the utility. So the consumers, the malicious consumers might be inclined to hack into them to lower their bills. So for that, the keys, the cryptographic keys and the procedures has to be secured at the hardware level on the end devices. And for that, typically we use secure elements, which are pretty much like the SIM cards or the embedded SIMs. They have the same level of security, and we can use them with the LoRaWan devices to have the same level of security you enjoy with your mobile phones. And if you look at the network stack, you would see the bottom layer, the physical layer, is LoRa. And there's always this confusion, LoRa versus LoRaWan. Well, LoRa is the physical layer. It's the name of the modulation. LoRaWan is the link layer that rides above that, and that's what we standardize in the LoRa Alliance. And right above that, we have placed the applications. When you look at that, what you would notice is something is missing. Well, some well-known layer is missing. It's the IP layer, the Internet Protocol layer is missing. Even though we're talking about Internet of Things, we are not using IP. The reason we're not using IP is because our payloads are so small over the air, as low as like 11 bytes, carrying IP header would be a significant overhead for us, like 20 bytes of IPv4 or 40 bytes of IPv6 would be just such a big overhead. So what we have done is we said we don't need IP. We can certainly translate or encapsulate the payload inside IP in the backbone, and we do that all the time, but we don't need to transmit IP over the air. And again, this is already done by Zigbee, Z-Wave, BLE does that as well. And even Narrowband IoT has this NIDD, non-IP data delivery mode, in order to have a very slim version to basically compress the payload. Well, having said that, for those who will really like to run IP end-to-end, we have collaborated with IETF in the LPWAN working group. We have, along with the IETF people, worked out IETF protocol, which basically has the ability to carry IP end-to-end, but over the air, it's like super compressed. If you look at the byte stream or the bit stream, you cannot recognize IP, but then there's this compression and decompression to decompress it into full IP header on the receiving side. So IP is also available as an option for the application that needs end-to-end IP. Adaptive data rate is the algorithm we have with LoRaWan. So basically the sensor, whenever it's far away from the LoRa gateway, or if it's behind, say, several walls in a challenging RF condition, it reduces the transmission rate, and then it increases the transmission power. That's the only way it can get its message through. But when it gets closer to the LoRaWan gateway, the network detects that, and the network tells the end device to start using higher transmission, higher data rate and lower transmission power. That way, we have two benefits out of that. One is the device can consume power. If it is very close to the gateway, it doesn't have to use a low data rate or high transmission power. By doing just the inverse, it's able to conserve power. And also by using a higher data rate, we can make this network scale even higher, because now more devices can be transmitting at the same time. So through that, we have this dynamically adapting networks. As the devices get, as we get more and more devices in the field, we will be dropping in more and more gateways, including picocells, and the long-range communication will start converging to short range with the availability of nearby gateways. And through that, we'll be able to scale this technology to near infinity. So that's also another powerful feature of LoRaWan. If you look at the deployment types, like I said before, you can have private networks and public networks. The private ones can span as small as residential areas, like a home, like an apartment, to a building, to a university campus, to a district, or the whole city. And then the public networks, where businesses build the networks in order to sell subscription. They can build citywide and also nationwide networks. And we already have several examples of such networks. Today, there are in fact more than 140 public networks around the world, all the way from California to New Zealand. And among them, there are several tier 1 cellular operators as well, such as Orange, Swisscom, NTT, SK Telecom, Tata, Enforta, etc. So for several such operators, LoRaWan is it's like a tool in their toolbox, right? They deploy both LTE-M and LoRaWan, or both narrowband IoT and LoRaWan. And depending on the use case, they can offer one, other, or both to their subscribers, to their customers. And it's up to the customer to pick and choose which one of these technologies to use for a given use case. And if we look at what kind of coverage operators get out of that, so this is Netherlands. It's practically fully covered by KPN. And this is Belgium, covered by Proximus. And this is Switzerland, covered by Swisscom, except for these white areas. And I'm sure you would appreciate that because of the Alps. These are the most inhabited areas. They are challenging, inhabited, so there's not a really good return on that coverage investment. So you can consider this as one of the most challenging terrains, and this is what Swisscom has. And in all these cases, more than 95% of the population is under the coverage of these operators with LoRaWan. And these networks have been up and running for more than 3-4 years already. And not only there are networks, but they are already peering with each other for roaming. We have this platform called Theme Park Exchange, TEX, abbreviation. And we have several LoRaWan networks on that platform, which is basically the backbone of LoRaWan at the moment. Most of them are public networks. We have a private network. We even have satellite networks, one of which is providing LoRaWan. The other one is providing its own proprietary connectivity. And we have what we call a joint server, which is like a centralized security server that holds long-term keys and that runs the authentication procedure. And these platforms are all connected to this ThinkPark Exchange platform, and they are able to peer with each other in order to provide roaming and also remote activation, meaning remote authentication. And this web of LoRaWan networks are spreading every month. All right, so if we look at what's behind all of that, well, behind all of that is an industrial alliance called LoRa Alliance that's been around for a little more than 5 years. It has more than 400 industrial members. It also has members from academia, by the way. Actually, the universities can become a member without any fee. We have this institutional member program, and in the alliance we have 3 committees: marketing, certification, and technical. Technical committee is the one where we develop the standard, and that's the one that I'm chairing. And as an institutional member without any fee, you can come and join these committees and contribute to the development of this technology. And among the members, we have all types of members, actually. We have cloud companies like Amazon, Alibaba, Tencent. We have telco infrastructure companies like Cisco, Intel, ZTE, Sagemcom, NEC. And we also have operators like, as I mentioned before, Orange, SKT, BT, Tata, etc. And industrial members like Schneider. It's a very diverse alliance, and it's also growing pretty fast in parallel with the adoption of this technology. And then if you wonder in physical terms what these things look like, a microcell is basically a piece of hardware like, this big, basically, with antennas. And these are the kind of gateways you would place at the top of rooftops and also on the towers, and that's what you get, like miles and miles of coverage. And then for your internal use, like in your home, in the lab, inside the buildings, you would use picocells, which look pretty much like Wi-Fi access points, both in terms of the form and shape and also the price points. And then for the R&D activities, you can also find development kits. These are also gateways, LoRaWan gateways, that you can have open source code and then build your own stack on top of that. So the technology is pretty accessible in terms of availability and the price point. And let me talk about some of the deployments already. So those networks that's been deployed for like 4 or 5 years, they're already serving industrial customers all around the world. So this example, this is a water utility company, Veolia. It's an international company. So they've been using wireless M-Bus for a long while. And after the development of LoRaWan, they have assessed this technology through a couple of years. And at the end of their assessment, they realized that LoRaWan is the right technology for water metering. It's low power because there's no power supply on the water meters, and it's long range, and it can go through walls, and it's also very low cost. So it's ideal. So they started migrating their meters onto the Orange's public network in France. So 3 million water meters. Now they are in a time span of, I believe, 4 or 5 years, they'll be migrating their devices onto LoRaWan. And not only the meters, but also the rest of the water utility infrastructure, they are able to monitor using LoRaWan. And it's not just in France, but we also have several similar examples throughout the world. And not only water metering, but also gas metering is a very key use case, especially with the ability to control the meters. For example, in case of an earthquake, you can shut off the valves by using physical broadcast feature of LoRaWan, and that comes pretty handy in order to prevent follow-up disasters after an earthquake, like fire breaking out. So there's a lot of momentum in the metering, which is also an essential part of smart city. Once you build the network and connect the meters, you can use the exact same network to connect all other sensors and actuators, which is the case in Shanghai. Already we have more than 300 sensors, like smoke detectors, like sensors monitoring the water quality in the rivers, and parking space sensors and manhole cover detectors. Manhole covers are also particularly interesting because there's like a lot of wiring going underneath, and thieves go after those assets and they steal the wires. So in order to prevent such unauthorized access, utility companies would like to monitor the manholes. And then asset tracking, personnel tracking and asset tracking is key in order to build trackers that can last longer using LoRaWan as opposed to GSM-based technologies for long range is really key here. Or unlike Bluetooth and Zigbee Z-Wave, LoRaWan can provide a really long range in open space area, and that's what you see in this example. In this example, there's a construction managed by Petrofac. It's an oil refinery. In order to track the location of the workers, they have these trackers in a large area that tracks 1,000 combination of personnel and assets with different types of trackers for heavy machinery as well. And then another case is Volvo trucks being tracked at a manufacturing facility in France. Large area, many trucks going through production process. At any point in time, they would like to know where each truck is. So to track their location, they have to rely on industrial trackers using picocells at the site. And again, now the pandemic situation created another use case to have a proximity alert and back tracing. And for that, now these trackers are equipped with an algorithm to beacon their presence and also detect the beacons from nearby trackers and report them using LoRaWan to the cloud so that we can track proximity throughout a period of time. And that's another unfortunately, rapidly growing use case we have for the LoRaWan trackers. And this is another use case. There are these electric cabinets throughout various countries in Europe. They are built by Schneider, and Schneider wants to track various conditions in these electric cabinets, like unauthorized access, like loss of power, or smoke and fire. And inside the electric cabinet, they use Zigbee sensors, but these Zigbee signals are aggregated on a LoRaWan device that is connected to the public network in that country. And these devices are scattered across France, Switzerland, Netherlands, Belgium. And through roaming, wherever they are, their traffic gets demodulated by the local public operator and pushed to the core network of Schneider. And we also have a pretty good momentum on the building management with occupancy, temperature, and air quality sensors throughout the buildings using picocells to collect this data and report on a dashboard. And just briefly about the company that I work for. Actility is a French company. We have customers all around the world. We are the leading LoRaWan system vendor. We build the core network that runs the not only LoRaWan, but also cellular IoT and satellite networks. More than half of the LoRaWan public networks around the world are using our theme park core network platform. We are also one of the founding members of LoRa Alliance with several leading leadership positions with a large developer network and a B2B marketplace. And the reason I particularly wanted to introduce this technology to my young colleagues like yourself is, now on one side we have this very fresh and challenging problem space. If you look at the requirements that we have to satisfy, it presents a very unique set that has never been taken up in the past. For example, using this technology, you can send only a small number of packets due to the ISM band limitations like duty cycle and dwell time limitation. Yet, you're supposed to provide connectivity for devices with a very small battery, but they're supposed to have autonomy for like 5 and even more than 10 years. They can only send small packets, like tens of bytes, and they should support long range, yet it should be very secure because the kind of assets you're protecting might be like securing a building or securing a meter or other financial assets. Using the ISM band, which is shared, there's really no owner of the ISM band. And there's an asymmetric network capacity. The uplink and downlink capacity is asymmetric. The downlink is usually more scarce, especially in Europe. And you're supposed to reach high scalability, like millions of uplinks you're supposed to support, because if you have a gateway that has like miles and miles of coverage, the chance of having like millions of sensors in that miles of range is pretty high. Even if not today, it's going to be high in a couple of years. And then there's a very wide range of use cases and traffic patterns. It's not like the mobile phone where you have like web browsing, email, video streaming, audio streaming, and a large file download, like 5 or 6 different use cases. The kind of use cases you encounter with, say, smart city, like connected vehicles, like utility networks, like health, etc. Every one of them are so different. It's really difficult to say, oh, okay, I'm going to cover these 5 cases. No, you would. With a network like that, if it is a public network especially, you'll have to cover like hundreds of different use cases. So that is a very unique set of problems. So that means it's a challenge, and challenge means an opportunity for the academia and for the startups or for anyone who is eyeing innovation. And on the other side, we have an open standard. The link layer is fully open. There are open source implementations for the end device and also for the network. And there are free developer tools. You can access the various network server platforms like Actilities and others free of charge. And the hardware for the end device and for the gateway is pretty low. It's very accessible. And in order to operate this technology, you don't need to have a license. So if you are doing some R&D on a GSM-based technology, like say you're building 6G, right? And you will be using some, or 5G, you'll be using some frequency. Well, those frequencies to operate those equipment, those are licensed. So you'll have to either have a license, but if you're not an operator, then you'll have to apply for a special permit for that band in a given region. Only after then you can use that. But with LoRaWan, it's just like Wi-Fi. You can buy equipment from an electronic store or order it online and then just plug it anywhere you like. One thing you need to pay attention is if you're in Europe, you should have an EU 868 megahertz equipment. In US, you should use US 915. You should not mix and match. You cannot use 915 gateway in Europe and vice versa. That's the only thing you need to care. And then if you're using standard equipment, it'll already comply with the regulation unless you hack it. You can, I mean, in a closed environment, you might be hacking it, but the off-the-shelf equipment will also be compliant with the local regulation. As such, you can just use it freely and safely. So, well, 45 minutes right on, and that's all I wanted to share. Now I can take some questions. I hope you have many questions to ask.
Well, there are at least 7 of them.
All right.
So I would like to start the first one, which received the most votes. What are the latency expectations of the LoRa when compared to the other tech like Bluetooth and Wi-Fi?
All right. So the transmission latency. Now, when we look at the latency, there is latency over the air and there is latency over the backbone. Now, in terms of latency over the air, we're using RF, right? So in terms of transmission, it is as fast as any other radio technology. But now, unlike cellular IoT, the band we're using is not licensed. It's a shared band, meaning that at the time I'm transmitting, someone else might be transmitting. And then there might be a collision. And for that reason, my uplink frame may not get to the network. And for that, we have several tools to mitigate this. But in the worst case scenario, the uplink doesn't go. And if the delivery, if I expect a reliable delivery, I would mark a bit saying that I'm expecting an acknowledgement. If I don't get an acknowledgement, I would retransmit. Again, this is very common with the other technologies as well. So due to the possibility of a collision, if I have to retransmit, then my frame would be delayed. So it might be delayed like a couple seconds, like tens of seconds, etc. For that reason, what we say with LoRaWan is we do not support real-time communication. For example, you want to control a drone, right? You want to press a button, or you have the control, and then you want to steer it. You would not implement this using LoRaWan. Because of what I just said, there's no real-time support. Or like what the 5G people say, like remote surgery. You know, the patient is across the globe, and then the doctor is in, say, US. They're doing remote surgery. You would not conduct a remote surgery using LoRaWan.
Yeah. So, but again, it is mainly for the sensor network. So you are collecting data from the sensors. Second question, again, with the most votes, why to use LoRaWan in private network instead of the low range alternative? So you mentioned that you use LoRaWan at home. So why to use it at home instead of Wi-Fi or Bluetooth?
Right. So compared to Wi-Fi, LoRaWan's advantage is low power. I mean, with the Wi-Fi, Wi-Fi consumes much more energy, and LoRaWan's power consumption is much lower. So, I mean, if you want to operate, if you want to have better operated sensors, typically at home people don't use Wi-Fi; they use Zigbee, Z-Wave, or Bluetooth. So for better operated, Wi-Fi is out of the picture. And then you would say, well, okay, if you can use Bluetooth, Zigbee, Z-Wave, why not already use them, right? Now, compared to them, even though the better consumption is similar now, LoRaWan's other benefit kicks in, the long range. So for example, with Bluetooth, you can hardly penetrate through one wall, right? And with the Zigbee, Z-Wave, you have a range of like 100 meters. You can go through a wall, maybe one or two, but not more than that, and then you have a range of 100 meters. With LoRaWan, you can penetrate through many more walls and also have a much longer range. So if you look at the latest announcement of Amazon, the Sidewalk, they have this product called Sidewalk. So Amazon has been serving sensors at home, and recently they have added LoRa to that connectivity. Why? Because they would like to have the home network to penetrate through walls and then leak into the neighborhood. Say your pet runs away, right? And it has a collar. Now you want to find your pet. Now, through this network of yours and your neighbors that goes beyond your residence and onto the street and beyond, then you start building a much larger coverage that helps you track your pets and kids in the neighborhood. And if you have a big, yard, you can also have coverage on that for like various sensors you have. So it's a combination of the range and the power consumption that the combination LoRaWan has puts it ahead of any of Zigbee, Z-Wave, Bluetooth, and Wi-Fi. Obviously, it's not going to replace any one of them right away. But when you need both the range and the low power, it has a unique position. And it is already starting to penetrate into home at the moment, as you can see from the sidewalk announcement of Amazon.
Yeah. Next question: are the bigger gateways compatible with the SDN UNOS Open Daylight type controllers? So, how the gateways are working basically?
Yeah, I mean, so far the gateways, the base stations, right? So so far we don't have any of that. I mean, I have not encountered anyone using SDN Open Daylight. So far they are a bit legacy, let's say. The most of the innovation, well, I shouldn't say that because I don't want to put the wrong light on the gateway vendors. Most of the LoRaWan intelligence is in the network server. The gateways, what they really do is they demodulate the frames from over the air, and then they encapsulate that in some other protocol and then push it to the cloud without really processing anything at the LoRaWan layer. The full link layer processing is happening at the network server, which typically resides in the cloud. So unlike Wi-Fi access point or unlike, say, 3, 4, 5G base station, we do not process any link layer. So it's relatively low weight. And the reason we do that is to keep the gateways low cost so that they can be ubiquitous. Because at the end, now they're getting into the home, and eventually they'll get into the appliances, and they will be in several assets we have at home to provide a super dense network in order to provide the all the advantages that I mentioned under the adaptive data rate feature. So yeah, they are pretty low-cost elements, and they don't do any link layer processing as such. So far, I haven't seen anyone using SDN or ONOS or Open Daylight on those piece of equipment yet.
Thank you very much. So next question. Can LoRaWan handle multiple continuous streams / flows of data in an effective manner with the degradation of throughput in the network? The question mentioned about the multiple camera inputs, but of course the data rates are not good for the camera inputs. But let's say you have multiple sensors in one device, and then you are sending this one through the LoRaWan. So what happens? Right,
exactly. So I mean, we can support zero camera.
Yeah,
there's like few bits like super pixelized from our old generation images. Now you can certainly support like thousands and thousands of devices. So a given gateway, a Microsoft gateway, can support in the order of like 60, 70,000 devices in its coverage area when those devices are like sending 1 frame an hour. So typical use of IoT that we're catering is a low bandwidth application. Like the most demanding application is the trackers. I'm just looking at, like this tracker, okay? Now, in the extreme case, this tracker can send its location like once every 2 minutes, okay? Now, in order to send it like once every 2 minutes, it just consumes very little bandwidth. And that's how we are able to scale this network to pretty high numbers. Now, on top of that, we have like multiple channels and like, 8, 16, and in US we have 64 different channels. So these devices are picking random channels for transmission. On top of that, even if 2 devices are transmitting at the same time on the same channel, if they're using different data rates, the LoRa gateway is still, in most of the cases, capable to demodulate 2 signals separately. So there are like several of these tools, techniques that come together to ensure thousands of devices can still be served by a single gateway. And having multiple gateways with macro diversity, we're able to support like millions and millions of devices in a given region.
Thank you. So, well, as a marketing person, maybe you might not want to answer this question, but which struggles do you foresee with a broad implementation of LoRa applications?
Which struggles? Well, let's talk about the. Okay. Let me ask this question this way: if it is so great, why do we not have billions of devices already? Why isn't everyone using LoRaWan today? Right? Let's put it this way. So now this is a relatively young technology. It's been around 5 years. Okay. Now, and it has a really good ecosystem. It's still flourishing, but now there's a challenge with IoT. For IoT to work, a lot of things have to come together. It's like a chain, right? You have to have a device with a sensor, with a radio, with a gateway. It's integrated to its core network, which is integrated to the application. And then there needs to be a system integrated, putting all this together. Everything has to work. Everything has to be reliable, low cost, secure. And then this has to be introduced to the customer. Now, customer needs to have an immediate pain. Customer needs to be open to new technologies. So you have to satisfy every piece in this chain to bring this to the market. Now, we're already able to crack that, and we're seeing a lot of examples, a lot of deployments like I have seen. But the reason it's not happening all around the world is making this chain work for every use case is just taking time. And the use cases are so diverse. You make this chain work once, then ideally you would like to resell this, right? Then you have to find the next customer who wants the exact same chain. Well, you know what happens? You go to the next customer, they go like, you know what? I'm not using AWS, I'm using Google. Or they go like, I don't want to use that gateway, I want to use this gateway. They change just one of the rings in the chain. Now you have to build this again, and that's a lot of pain, honestly. That's a lot of pain. And then if you start moving on to the other use cases, the whole chain is different. The sensor is different, the gateway is different, cloud is different, application is different. And on top of that, there's a resistance. You're trying to automate a process where this company has employed like 10 people for that. Now they're going to lose their job, and there's this resistance to that. So that's why this whole IoT is growing real slow. And among that, actually, LoRa's momentum is faster than the IoT's overall growth, but still it looks slow to the people who are, say, involved in blockchain, AI, robotics, going to space. IoT has been around for like 40 years. Tracking vehicles, that's what Qualcomm has started with. Their first product back in 1985 was tracking trucks in US. And that's IoT, right? And we're still trying to do that. But we're trying to do it for the masses. That's why we call it massive IoT. Now we're trying to bring this to the masses, to that promised land, the billions of devices. But it is taking time. It's not an easy task. A lot of engineering, marketing, sales, engineering, and science behind that all has to come together. It's exhausting, I have to tell you.
I'm sure. So one next question was about actually the gateway prices. Do you believe that your gateways are expensive?
Yeah, well, they're not. I can provide some price points just as examples. So today you can find picocell gateways, like the home access point types, below 100 euro. And then the microcells you can find, I believe, around 1,500 euro or less, depending on the volume purchase. So yeah, these are the price points really. Compared to like cellular, the microcells are like 1/5 or 1/10 cheap, and the picocells are like converging towards Wi-Fi access points pretty fast.
I see. Well, we received an extra comment on that. Probably like there's a waiting period for the deployment of the gateways, or is there some bureaucracy, or can I buy a gateway right away from any vendor?
Well, okay, yes. You can, depending on where you are and what RF region you are in. Let's assume you're in Europe, right? You can buy an EU 868 gateway. There are like at least 15 different brands, 15 different companies building these gateways, and you can already purchase them and then plug them and you can use them. I mean, for example, if you go to market.thinkpark.com, that's my company's marketplace, you can find them. And there are also several other resources. Now, if you are in a country where the regulation is not clear, then you may have to wait for that. But those are somewhat rare. I mean, like North America, South America, definitely across Europe, it's all set. I mean, China, South Korea, Japan, Malaysia, New Zealand. Yeah, we have all those countries all set with the regulations. So can I ask which country are you asking for?
I believe from Turkey.
Turkey, don't worry, you can buy one.
Okay.
There's no issue with using them. But if you want to be a service provider, then like say a nationwide coverage or even as a citywide coverage, and then if you want to sell subscription, then you are subject to another license, but it's not about the RF. So today, for example, we have a macro cell. Actually, that's a good question. Let me answer it for our colleagues in Turkey. So we have deployed a macro cell at Istanbul Technical University Maslak campus. And you can already use that. You can create, I don't know where I should share. Can I share on the chat?
You need to go to the ask a question, then go to the answered questions, and he's in the bottom.
Maybe if I can put on the slide, I'm still sharing the slide, right?
Yeah, the slides are here.
Yeah, okay, let me put it here. If you go to this site, okay, community.thinkpark.org, this site lets you create a free account on our network server, ThinkPark community platform. And on that network server, you can already enjoy the coverage provided by the macrocell gateway we have installed at the Maslak campus, if you're in the coverage area, right? I mean, it also goes across the bridge. Well, okay, if you're not under that coverage, you can buy a gateway from here. And then you can use them for your own R&D purpose, for connecting your devices. But if you want to sell connectivity over that, then you are becoming like an ISP that requires license.
Okay. So next question, and I was actually thinking about that as well. Is there a soft opening and room to improve locationing accuracy? So you mentioned that for the tracking of the COVID and so on, the 20 meter is not good enough, probably. So you are using an extra solution, and on top, the LoRaWan actually informs the network. I believe that's the way you are handling it.
Yeah.
So what do you think? What are your opinions about this topic?
Right. So I mean, like on this tracker, actually, LoRaWan is the backhaul, but the geolocation we're using is not LoRaWan's own geolocation, because for like tracking personnel, tracking for proximity, that's not good enough. So instead, we are using a Bluetooth sniffer, Wi-Fi sniffer, and GPS receiver to determine the location and then transport that information using the LoRaWan backhaul. Now, is there room? What's soft opening mean? Is it a term?
So, like again, can you do something with the LoRaWan, maybe with the software change and so on, and improve its?
I see. Yeah, right. Exactly. So definitely, there's room for improving that. So I mean, if anyone is into like geolocation algorithms, certainly that's a nice area of research to improve the geolocation provided by LoRaWan. You can also consider doing combining that with Bluetooth, Wi-Fi sniffing, and GPS. Yes, there's room for research and R&D in that field. Yes.
So next question, is it possible to use multiple private networks in crowded cities like Istanbul without any problem? Isn't it better to use the low-range alternatives compared to LoRa?
Right, so that's a very good question for which I have a somewhat detailed slide. Is my slide big enough?
Yeah.
Yeah, okay, all right. So yes, definitely. Well, in those countries where we deploy LoRaWan, there are not only public networks, but private networks, and multiple of them all overlapping. For example, France, we have a nationwide network of Orange and also Bouygues Telecom, two nationwide operators. They cover the whole country, more than 95% of the population, overlapping public. And below that, there are other private networks, like your building has one, you have one, your municipality has one. They are all overlapped, and they all coexist at the same time. And how does that happen, right? How do they not interfere with each other? How do they not collapse all the networks? Well, we have a very rich toolbox and a lot of tools we have in the toolbox to make this happen. First one is microdiversity, the ability to have multiple gateways receive at the same time. I talked about that. Second one is this LoRa CSS modulation, the high immunity against interference. And we also use forward error correction, meaning that even if some frames or some bits are lost, there's enough redundancy in the messages to recover the lost bits. And it allows operating at very low signal to noise ratio, basically down to minus 20 dB below the noise level. So there's a lot of noise resiliency in that. And then another thing we employ is being compliant with the ISM band limitations, for example, duty cycle limitation. So duty cycle limitation in Europe says in certain bands, a device can transmit only 1% of the time or 0.1% of the time. For example, in a 1 hour period, like 3600 seconds, only for 36 seconds it can be transmitted. Then it has to shut up until the end of the hour. Only after that it can say something again, right? So basically there's this moderation. So it's not like everyone can stream and talk all the time. They already moderate. And then we have multi-channels like 8, 16 in Europe and 64 in US and in China. And being able to demodulate of different data rates at the same time, even if two devices are transmitting at the same time, we can still separate them if they are using different data rates. And then the ADR, again, as the devices get densified, we will naturally start deploying more gateways. As there are more gateways, they will end up getting closer to the device, and the device will start using lower transmission power. So this long range will start becoming short range. Like this sensor I have at home,
similar to cellular network, so.
Right, is using this gateway right on my desk or downstairs. It's not like shouting across like miles and miles. And then the usual confirmed, like expecting acknowledgements. And finally, we're also able to use this forward error correction at the application layer. For example, this low-cost temperature sensors, they're like transmitting the temperature reading every, say, 5 minutes. They are not asking for acknowledgement. Instead, they're just putting enough redundancy in every report so that even if you use like every third of the frame, you can still reconstruct the series in the cloud side without having to ask the device to retransmit again. So the collection of all these techniques basically provide this future-proofness. And that's how all these metering companies decide to migrate their meters, like millions of meters, onto these networks. They know these networks are going to get heavily used in the future, but thanks to all these techniques, we'll be able to cope with that. And just to give you this analogy, right? Everyone is using Netflix, like streaming over Wi-Fi. You're doing that, your next door neighbor is doing that, and upstairs and downstairs. Yet everyone is enjoying their show, right? So all of these are built into the radio technologies to deal with these challenges.
Thank you. You already actually answered the last question. What are the major advantages of the LoRaWan compared to Bluetooth, Zigbee, and 5G and Wi-Fi? I want to ask actually something else in that thing. So I mentioned that you are one of the leading persons in the IoT in Turkey. So there is a group, Nesnelerin Interneti in Turkish, what we call. So what are your activities there, and what do you suggest for the Region 8 members to do in terms of the IoT?
Right. So, well, yeah, Nesnelerin Interneti Toplulugu, it means the IoT community in Turkish. I had formed this, I think, a little more than 5 years ago. So the idea was that I've been working in this field for almost 10 years now on IoT, and especially IoT requires to have a ecosystem and a community. No single company, I mean, you could be one of the largest, like you could be Google, Amazon, you could be, say, Ericsson. You cannot build the whole solution end-to-end by yourself. It's this long chain, and no single company can build this chain single-handedly. So for that, you need to have an ecosystem. So that's one thing. And that's how all of the successful IoT technologies are moving forward, or the successful companies are moving forward too. They build an ecosystem and they move together. They nurture themselves and they move collectively. This is one thing. Secondly, second thing is the main innovation comes from startups. That's true across the globe, right? And then startups need a lot of help. They take a challenge that's like 10, 100, or maybe 1,000 times bigger than what they can really do. And for that, they need a lot of help. And there's a lot of insight they need to get. And building that insight by trial and error is too lengthy. The sooner they get the answers, the better for them to get to the finish line. So the best way to provide that help is to basically do this lot of, support them, do this clue injection, and then build an ecosystem around that. And then only through that, a local ecosystem can survive and then become competitive in the larger landscape. That's exactly why I started that activity. And then quickly, I had a bunch of other people joining me to form a group to support all these activities. Right now, we have more than 100 IoT startups in Turkey. It's a very lively ecosystem. We're adding a couple more every month, and then few are dying along the way, just like a living organism should have. And with this ecosystem, what we're doing is we're organizing a lot of events, like webinars where we have the founder of a startup come and give a talk, provide all the insight, which is not only encouraging to the newcomers and also insightful to other IoT startups, but also helpful to that presenter so that they can form partnerships. And then we have hands-on workshops to accelerate adoption of new technology, like we're doing LoRaWan workshops. And we're also working closely with academia in research and also supporting various IoT classes. And then also acting as a bridge between the IoT startups and the industry. Because always startups want to work with the industry and vice versa, but this is an extremely boutique activity. It's like matchmaking, right? I mean, there has to be a lot of chemistry match, and there has to be a lot of hand-holding to glue the two sides together. It's really hard to make it work. So we're spending a lot of time on these kind of activities to elevate our ecosystem so we can build internationally competitive IoT companies coming out of Turkey.
Okay, last but not least, you have already done it, but if our student and young professionals have more questions, how they can reach you?
Right. Please note my...
it was in the last slide.
Yep. Please note my email address here, and feel free to reach me by email anytime. Certainly, we'd like to see LoRaWan spread much faster in the academia. Well, like I said, this is a unique opportunity. I know most of you guys are already busy with other research, but if any one of you are looking for new research in communication technology, in RF, in security, I would strongly recommend LoRaWan for it being fresh and challenging. with the availability of the tools. So feel free to reach me or other colleagues in our larger ecosystem in other companies as well. There are a lot of areas we can fully leverage the talent and the expertise you guys have. So very welcome.
Thank you. I believe Simay is here. I would like to actually invite Simay Akar to the group as well. Online and... Okay, so yes, Simay is here too. So it's time to actually close the Student and Young Professional Congress. So as IEEE Turkey section, we have the honor. So Simay, floor is yours.
Thank you very much for the great presentation, firstly. And we have been privileged hosting this day, actually, as Turkey section. So as far as we know, this is the end of this amazing Congress for 14 days. So like with the collaboration of the whole Region 8 communities and young professionals, student activities, women engineering, and many other initiatives of Region 8, and also IEEE global communities. So we had a lot of support behind, and it was the final day. And as a Turkey section, so we have been the host, and it was really great honor. So we thank everyone behind this initiative on behalf of the section and also individually. All of us, we had really great time during this virtual Congress. So I just want to say, I want to just applause for everyone behind this initiative. I want to actually check if, let me see who is live. So I would like to invite Gerard, who is the chair of this Congress, to the screen. Gerard, are you there? Can I invite you on the screen? I know you're there. I'll try my chance.
Hello.
Hello.
Hi, how you doing? Thanks. I was caught unawares. Damn you, Samir.
Well, it was a last-minute surprise for you, but
yeah, very last-minute surprise. But we wanted to appreciate, like everything you do, all the team do behind. So want to give you a floor to say something before we close.
Yeah, in the times of the pandemic, very, very hard times and so on, but it was a great Congress, so we would like to thank you and the whole group as IEEE Turkey again.
Thank you very much. And I mean, like both you and Samir was saying, I mean, there's an enormous team behind this. I actually do so little. It's those guys that does all the work. Samir too has been working so hard during the whole planning process and everything. And I mean, all the ambassadors we had, all the different host sections, all the speakers, we had like over 100 speakers or something. All the attendees, we had like 2,000 people nearly registered, and everyone has been showing up and interacting with the speakers. It's, yeah, just a big, huge thank you to everyone. Magdalena and Antonio for organizing this and supporting us. I see Inez in the chat as well. She's been working away hard, and everyone on the team. Just a big, huge thank you. And yeah, special thank you to IEEE Turkey for doing a wonderful job in closing the Congress and providing us with some brilliant speakers and brilliant moderators and brilliant ambassadors.
So let's say goodbye together then. So
let's say goodbye together.
Have you got a cup of water ready, Simay?
Oh yeah, actually, so because this is Turkish tradition, so we we just throw the water behind the barrel. I was just joking about that, but actually, it. Yeah, we could have it. So we hope to see and meet with everyone by the first chance in any IEEE meeting. We have no doubt we will meet soon somewhere. So hopefully sometime sooner than we expect.
Hopefully. Thank you, everybody.
Thank you and bye.
Bye.